A motor with no magnets sound impossible. No copper coils, no spinning electromagnetic fields, none of the components we've trusted for over a century. And yet, scientists are now testing a machine that runs without any of them. Even stranger, the core of this motor isn't metal at all. It's made from material that behaves like both a liquid and a solid at the same time. Something that flows yet holds structure. Something that moves yet stays organized. At first glance, it feels less like engineering and more like science fiction. But this isn't a concept sketch or a distant theory. It's real, and it's already working in controlled environments, which raises an uncomfortable question. If this is possible, how much of what we think we understand about motors is actually incomplete? To make sense of this, we need to step back for a moment. Every motor you've ever seen, from a ceiling fan to an electric car, relies on the same basic principle: magnets. More specifically, the push and pull between magnetic fields. When opposite poles attract and like poles repel, they create motion. That motion is controlled, repeated, and converted into useful work. It's simple, reliable, and incredibly effective. You can think of it like two invisible hands constantly pushing and pulling an object in a circle. One side pulls it forward, the other pushes it away, and the cycle repeats. That's what keeps everything spinning. It's a system we refined for decades, and for the most part, it works beautifully. But what if you remove the magnets entirely? There's another way to create motion, and it doesn't rely on magnetism at all. Instead, it uses electric charge. You've experienced this before, even if you didn't realize it. Rub a balloon on your hair and stick it to a wall. Touch a metal doorknob after walking across a carpet and feel that tiny shock. That's electrostatic force. It's the attraction and repulsion between positive and negative charges. Now imagine harnessing that force inside a machine. Instead of magnetic fields pulling a rotor around, electric charges do the work. This is the idea behind electrostatic motors. And at small scales, they're incredibly efficient. In fact, devices inside your phone may already rely on this principle. But there's a problem. As you try to scale these motors up, everything becomes unstable. To generate enough force, you need extremely high voltages. Not just a little more, but thousands of volts. And at that level, the system starts to break down. Air stops acting like an insulator. Sparks jump across gaps. Energy is lost. Control becomes difficult. What worked perfectly at a tiny scale suddenly becomes impractical. So engineers found themselves stuck. On one side, a proven system built on magnets. On the other, a promising alternative that simply couldn't scale. And that's where things started to get strange. Because recently, researchers began experimenting with a completely different kind of material. One that doesn't behave like a typical solid or liquid. One that responds to electric fields in ways no one fully expected. At first, the results didn't make sense. The forces didn't follow the usual rules. Motion appeared in directions it shouldn't. It was subtle, easy to overlook. But if what they were seeing was real, it meant one thing. The limitation that held electrostatic motors back for decades might not be a limitation at all. What scientists uncovered next is where everything changes. The strange behavior wasn't a mistake. It came from a class of materials known as ferroelectric liquid crystals, and they don't behave the way normal materials do. On a microscopic level, their molecules line up like a solid, ordered and structured, but they can still flow and shift like a liquid. That combination alone is unusual, but the real breakthrough is how they react to electricity. Instead of simply being pulled toward a charge like in traditional electrostatic systems, these materials can generate force sideways. Not forward, not backward, but at an angle, a transverse force. And that tiny difference turns out to be the missing piece engineers have been struggling to find for decades. Because when force is no longer limited to a straight line, everything changes. The system becomes far more efficient at converting electrical energy into motion. What once required thousands of volts can now happen at a fraction of that. Suddenly, the biggest weakness of electrostatic motors begins to disappear. This is the moment where the idea shifts from interesting to transformative. Lower voltage means safer systems, simpler designs, and far less energy loss. But more importantly, it unlocks performance that wasn't possible before. Early experiments suggest that this new mechanism can produce significantly stronger forces relative to its size. In some cases, materials built on similar principles have demonstrated the ability to lift thousands of times their own weight. That's not just an improvement. That's a completely different category of capability. And once you start thinking about where this could lead, the implications expand quickly. Imagine robotic systems that don't rely on rigid motors and gears, but instead move with smooth, responsive precision, movements that feel less mechanical and more organic, muscles that react almost instantly to electrical signals, mimicking or even exceeding the responsiveness of biological tissue. This isn't just about efficiency. It's about redefining how machines interact with the world. Then there's transportation. If motors can be made lighter, simpler, and capable of producing strong torque at lower speeds without complex gear systems, entire vehicle designs could change. Electric vehicles, industrial machines, even small-scale devices could benefit from a system that reduces weight while maintaining performance. But this isn't a perfect solution. Not yet. The same properties that make these materials unique also introduce new challenges. Because they can flow, there's internal resistance. That limits how fast the system can operate. Push it too far, and efficiency starts to drop. There are also engineering hurdles in controlling and stabilizing these materials over long periods. And while the voltage requirements are lower, precision in how the electric field is applied becomes much more critical. So while the potential is enormous, the technology is still finding its footing. And that's what makes this moment so interesting. We're not looking at a finished product. We're looking at the early signs of a shift. The kind of shift where a single discovery changes the direction of an entire field. If new variations of these materials can be developed, if their limitations can be reduced even slightly, the ceiling for what's possible rises dramatically, which leaves us with a question that's hard to ignore. If this is what we can do now, with a material that was barely understood not long ago, what happens when we truly learn how to control it? Because this might not just be a better motor. It might be the beginning of something entirely different.